Do you need a roadmap for Calculus 2? Curious about what lies ahead? Hi, I'm Jen, founder of Calcworkshop, and I'll be guiding you through Calculus 2, starting with part 1 of our 6-part series, Integration. Let's get started. So what's integration? Well, integration is nothing more than taking small parts and adding them together. So in Calc 1 or differential calculus, we took something and we broke it down into smaller pieces. In integral calculus, we're going to take those small pieces and put them back together again. That's why integration is also referred to as anti-differentiation. We're going to take the antiderivative or the inverse operation. We're going to put those pieces back together again. So now, how do we do that? Well, we start off with this idea of what's called a Riemann sum. So the great thinkers of our day realized that putting things back together again is in essence finding the area under a curve from the curve to the x-axis. So the goal is to find this area from f of x to the x-axis for a finite window, a finite interval from a to b. Well, we know it's kind of misshaped, but we don't really have a good way of finding it. So we refer to our geometry skills. We know how to find the area of a rectangle without pretty much any issue. We know it's just base times height or length times width. So we can make one big rectangle and we can find the area of the rectangle. But it's not very accurate. Well, instead of making one big rectangle, maybe we make 2 rectangles. Okay, it's better, but still not great. Well, the more rectangles we make, the better accuracy we get. And depending on whether the function is increasing or decreasing may change which way we create our rectangles. And why stop at rectangles? Couldn't we change the shape into maybe rectangles, from rectangles into trapezoids? There are so many different possibilities to create an approximate estimation for the area under the curve. But it's still an estimation. Can we make it any better? The answer is yes. We can take what we learned from Riemann sums and we can say, you know what, if we have this finite number of rectangles where we take the rectangle, the height of a rectangle, and multiply it by its width, so base times height, length times width, we can find the area of a rectangle and we can have it for a finite number. But if we can then take the limit as n approaches infinity, we can turn this finite number of rectangles into an infinite number of rectangles. And that is a great way for us to estimate the area under the curve of some function with respect to x. Notice all we're doing is taking that sigma notation and elongating it into an S-shaped integral symbol, and that's really what's happening. But more importantly, the limit of finite sums, or sigma notation, is the way to take these rectangles and take the estimation and make it extremely accurate using what we know about series values. That we know if we have a specific number of rectangles, we can actually use converging sequences in series to actually come up with the accurate answer for the area under the curve. But this is kind of tedious. Do we have to do this every single time for every single value that we want to integrate? Well, we had derivative rules, like the power rule, the quotient rule, the chain rule. Maybe there's integral rules. So what are the integration rules? Well, first, let's talk about the 2 different types of integrals. There's something called an indefinite integral and a definite integral. An indefinite integral doesn't have limits or a finite interval from a starting value and a stopping value, whereas a definite integral starts at some point and stops at some point. The indefinite integral is referred to as the antiderivative or anti-differentiation. So whenever you hear that phrase, you're thinking indefinite integral equals anti-differentiation. A definite integral is an integral, but we use the word integral lovingly for both. So when you hear integration, it's referring to both indefinite and definite, but technically indefinite is the antiderivative, definite is the fundamental theorem of calculus, because what's happening is for the indefinite integral, you're getting a family of solutions. You're going to get the function, so you're taking a derivative and getting the original function. For a definite integral, you're getting a numerical answer. You're finding the actual area under the curve from A to B. Now, there are properties that we are going to learn along the way. Well, we learned that we could take a derivative of each term individually. Well, we can integrate each term individually. We can pull out a constant and multiply by that coefficient at the very last minute. So we can pull out a constant outside the integral and then evaluate at the end. But more importantly, the most important rule in derivatives was the power rule. Well, the most important rule for integration is the power rule in reverse. So with derivatives, we brought the exponent down and decreased the exponent by 1. So we multiplied and decreased the exponent by 1. This time, we're going to do the complete opposite. That's why it's called the anti-differentiation, antiderivative. Instead of bringing the exponent down and decreasing the exponent by 1, we're going to increase the exponent by 1 and then divide. So this becomes our new amazing rule. We're going to increase that exponent by 1 and divide by that quantity. I'm going to add that plus c because it's an indefinite integral, or the antiderivative, for a family of graphs. But just like we learned in derivatives, there's more than just the power rule. So what other rules are there? Well, there's integral rules for exponential functions and also logarithmic functions. Remember, with the derivative, for the exponential, we rewrote it, and then we multiply by the derivative of the exponent and the natural log of the base. We're going to do the opposite. We're going to rewrite it, but instead of multiplying, we're going to divide by the exponent coefficient and the log of the base. We're going to add that plus c for the constant of integration. For the natural logarithm, we know that the derivative of the natural log of x is 1 over x. So doing the antiderivative, taking the derivative of 1 over x and integrating it, we go right back to the original function. But there's also trig rules as well. So for our trig integrals, we have to remember that we're doing the opposite of our derivatives. So if we knew that the sine function, the derivative of sine was cosine, the integral of cosine would have to be a sine function. So the integral of cosine ax is sine of ax divided by a. Remember, we're doing the opposite. So instead of multiplying by the coefficient, we're dividing. Well, if the derivative of cosine was a negative sine, well, the integral of sine would be a negative cosine. And again, dividing by that coefficient instead of multiplying by the coefficient of the angle. And if we know that the derivative of tangent was secant squared, the integral of secant squared is tangent. Again, dividing by that value. We would learn all the different techniques for how we can simplify using some rules from trigonometry along the way. So are there other techniques out there? Sure. What about the inverse trig functions? So the inverse trig functions, once again, we're taking what is the derivative and reversing the operation, taking the antiderivative. So for the arc sine function, we knew the derivative was 1 over the square root of b squared minus ax quantity squared. Well, taking that in reverse, if we see a function that looks like this, we know in reverse direction it's going to be 1 over a, because again, we're not multiplying by the coefficient, we're dividing. And it would be the arc sine of ax over b. And we have our arc secant, and we have also our arc tangent. We only need to memorize 3 of them because the other 3 inverse trigonometric functions are just the negative of them. What's also important to recognize that these formulas that you're going to see in the back of your textbook won't have a and b because it only refers to when the value is 1, when we have b is 1 or a is 1. But that's not always the case. What happens when b is something other than 1 or a coefficient is something other than 1? These formulas help to solve all different types of functions, not just the ones that you see in the back of your textbook. But there's even more out there. What do we do with when we want to actually take the derivative of an integral? Let's look about that. All right, so the fundamental theorem of calculus we know helps us to calculate the numerical value for the area under the curve. We have a starting value of a heading to b of some derivative, some function. So to find the area under the curve, we integrate and then we plug in our upper and lower limits, and we get f of b minus f of a. So that's the fundamental theorem of calculus, referred to as FTC number 1. But what about another form of that rule? What happens if we want to take the derivative of an integral? Well, a square and a square root cancel each other out. So wouldn't a derivative and an integral cross each other out if they're inverse operations? And they do. The derivative and the integral say, hey, you don't actually have to integrate just to turn right back around and take a derivative. But we do have to handle, we want to take the derivative of x, and that's a function in terms of t. So we have to plug in our limits, but not forgetting to take the derivative of whatever we plug in, because again, we're taking the derivative of an integral. But gosh, this looks really familiar. This looks just like the chain rule, where we've got a function on the inside and its derivative on the outside. How do we handle something like that? Let's find out. All right, so U substitution is the way we deal with composite functions. So we've got a function inside of another function. But more importantly, it's the reverse of the chain rule, where we've got this inside piece and the derivative on the outside. Just like we saw when we would rewrite and then multiply by the derivative of the inside, we're going to do the opposite operation. but it's way too complicated. So instead we're going to use a substitution. We're going to create a new function based off of the pieces that we see. We're going to take that inside piece and we're going to let it be a u. But if we're going to turn everything into a new letter, we have to change the function into a new letter, which means we have to change our dx into a du. So what we're going to do is we're going to learn how to create this new function in terms of u by making let statements that are based off of the composite function that we see. The cool thing is we only need to find two places that we need to replace, and everything else will fall in. And that's the beauty of u substitution. And the u substitution function is going to be seen in all other types of substitutions that we're going to see throughout integral calculus. But what happens when we want to look at something more real world? What happens if we want to take these functions and these rules that we've seen and talk about average values, average rate of change? What about that mean value theorem that we learned back in differential calculus? How does all of that play in? So the mean value theorem, it allowed us in differential calculus to be able to find out when the slope of the secant line is equal to the slope of the tangent line, the average rate of change equaling the instantaneous rate of change. Well, we have something very similar in integral calculus. What we have is this area under the curve. Well, there is a point somewhere in this interval where there's going to be a point C, where this point C is going to be able to help us create a rectangle, that the rectangle is going to have the exact same area as the area under the curve. So what we are going to find is that we have this 1 over b minus a integral from a to b of f of x dx. This is, in essence, the mean value theorem for integrals. What we call is the average value function. So just like we saw in differential calculus, there is some value c within the interval that we can find that the slope of the tangent line equals the slope of the secant line. In integral calculus, there is some value c in the interval that's going to help us find this height of the box, f of c, this height of the rectangle, that this rectangle will have the same area as the area under the curve, which is pretty cool. But why stop there? Can't we also apply that to particle motion? What happens in real-world applications? Can we use integrals to help us write functions like velocity, acceleration, and distance? So if definite integrals help us to find the area under the curve, couldn't definite integrals also help us find the distance traveled? Yes, absolutely. In fact, the position function is just the integral or the antiderivative of the velocity function. And the velocity function is the integral or the antiderivative of the acceleration function. By integrating the derivative, we get that original function, which is helping us to find distance traveled or overall velocity or even speed. What we can actually then write are definite integrals. If we have an initial condition, we can then say, hey, when x equals time of a, and we know we're position b, then how we find how far we've traveled after a certain time interval, we can use integration to find those values. So not only are we not only finding area under the curve, but we're finding distance, which will then help us to find arc length functions and surface area and solids of revolution and three-dimensional shapes, which is super exciting. But let's take a pause. Let's remind ourselves of where we've been before we tackle on more of how we can actually use integration to help us solve some really complicated stuff. Let's take a look at Simpson's rule. So Simpson's rule is not a topic that is always discussed in a Calculus 2 class. In fact, every high school student, you don't really even cover Simpson's rule. It's an extension topic that could be used but isn't going to be covered on an AP exam. College students, your professor may decide to do it, may not. So you may or may not see it. It's a wonderful pause before we jump into really separating like AB calculus and BC calculus or the more advanced integration techniques. What it is saying, hey, you know, we learned all of these great things, but are there other ways that we can kind of review and talk about the error involved of what we've actually been finding? So we learned the midpoint rule, the trapezoidal approximation, Riemann sums left and right endpoints. But there's error involved in those approximations, and so we will discuss the error involved. In fact, these error-bound formulas are going to play a significant role when you get to sequence and series, where you're going to see something very similar when we talk about Lagrange error bound. So knowing these kind of rules and where these formulas come from and how we're finding max values of the derivative function and using the next unused term is going to play a significant role in your future understanding. So Simpson's rule is a wonderful way for us to kind of take a regroup and kind of figure out where we've been. Instead of using rectangles or trapezoids, it uses parabolas. So Simpson's rule is just the 1/3 rule sometimes is referred to. So we're taking 1/3 of the width and then multiplying those height values, but we're alternating between 4 and 2 of the coefficients. And we're making sure that that number of subintervals, the number of rectangles or parabolas that we're using would be an even number. But it's a wonderful pause in between what's referred to as, the more basic foundational integration techniques and the more advanced. So now that we've got that pause, let's jump to the advanced techniques, starting with partial fractions decomposition. And you're probably thinking, wait a minute, partial fractions, didn't we do that in pre-calculus? You did. We took a fraction that was maybe a nasty big fraction, and what we learned is we could take a big fraction and break it into partial sums. We can break it into smaller fractions, and we can add those fractions together to come back to the original big nasty fraction. Well, we can do the same thing when we've got a function, integrand, that's really nasty and it's a big fraction. We're going to take this big fraction and we're going to factor its denominator. Then we're going to take all of its factors and create little baby fractions, and we're going to figure out what those coefficient values would be, that if we added up all of these fractions together, we'd come back to the big nasty one. But what it's doing is taking something that we cannot integrate into something that we can by integrating each individual fraction separately. We're going to learn different techniques, remind ourselves of what partial fractions was when we learned back in pre-calculus, and use some advanced integration techniques to be able to take a fraction and integrate them. But this isn't the only technique involved. What about integration by parts? All right, so integration by parts is when we've got a function where we've got two things being multiplied together that are completely unrelated, like an exponential function and a trigonometric function. Well, what do we do with that? How do we integrate two things that are multiplied together that don't really kind of get along? Well, we have to use a technique where we can kind of separate some things out. We take a derivative of one and integrate the other to come up with a formula called uv minus the integral of v du. So we're going to learn a formula that's going to help us to integrate two things that are kind of mixed together. In essence, very similar to this idea that when we had implicit differentiation, you had x and y commingling together and you couldn't break them apart. Same thing with integration by parts. The key is figuring out what your u is and what your v is. And there's some really cool phrases out there. I like this one the best. So this helps us figure out what your u is. It's I'm late. So inverse trig functions, logarithmic functions, algebraic or polynomial functions, trigonometric functions, exponential functions. This fun acronym helps us figure out what our u value is, what our dv value is, and helps us to separate and integrate a function that's kind of all mixed together. But u substitution was the building block to get us there. But there's more substitution values that we can look at. Let's take a look at advanced integration techniques. So advanced trig substitution is when we've got products of trig functions that want to go together, but something's a little off. We've got sine and cosine, which we know go together. They're nice cofunctions. Secant and tangent, they go together. That's pretty nice. But we've got powers, meaning let's say we've got sine to the 5th, cosine to the 4th. What do? Well, we're going to learn how to create a substitution, or in essence, a u substitution, by being strategic on looking at what the powers are, which one's odd, which one's even. We're going to basically reduce the powers down using our trigonometric identities that we learned back in trigonometry and pre-calculus to help us to transform the integrand into something that's easier for us to manipulate. We're going to take trig functions and turn them into polynomial functions that we can totally integrate using our basic power rule in reverse. We're also going to learn how to take an integrand where we've got, let's say, different angle measurements. Sine 5x times cosine 3x. What do we do there? Well, we're going to revert back to what we learned back in trigonometry, where we knew we could change it into a product sum identity. And we're going to remember those rules to, again, transform our function. So we're going to learn how to take trigonometry or trigonometric functions and turn them into polynomial functions. But what happens if we've got a polynomial function and it's actually easier to turn it into a trig function? Let's look at that. So trigonometric substitution is when we've got functions that look like they're the inverse or arc functions for integrals, where they were in the denominator, then we can just use our inverse trig functions that we learned back in a previous lesson. But they're not. But they do look very familiar to us. They're binomials underneath radicals. And they have this strange familiarity to the Pythagorean theorem. We have this x squared plus y squared equals r squared. And if we solve, let's say, for x, we would subtract the y squared. X squared equals r squared minus y squared. And if we take the square root, we're talking about a binomial underneath a radical. And that's very similar to what we're seeing. More importantly, if we can see that the similarities between Pythagorean identities, we can also use SOHCAHTOA, where we can actually talk about angle measurements. The sine is the opposite over hypotenuse, cosine adjacent over hypotenuse, tangent is opposite over adjacent. We can use everything we learned from geometry and trigonometry to help us transform this function that looks very similar to the Pythagorean theorem and turn it into a trigonometric identity, what we can actually go ahead and integrate. And that's the idea behind trigonometric substitution. Again, everything kind of goes back to U sub, but different techniques of U substitution as we progress. So there's only one more integration technique that's out there. What do we do when it's improper? Meaning we want to take the integral of an indefinite value, meaning not from a starting point to a stopping point, but something that's infinite. So improper integrals or improper integration is when we have limits on our integral that are infinite, meaning, well, it's not a tangible number, so how can you plug in infinity? We don't even know what it is. So we think back to what we learned in differential calculus, and we said, hey, limits. We don't have to touch infinity, but we can approach it from one direction or another. So we're going to transform an improper integral into a proper integral where we've got limits a and b, tangible values that we can plug on in, and then once we integrate it, we'll apply a limit, basically looking at end behavior. For some functions, we'll recognize that it's going to converge, it's going to work. Other times it's going to blow up, it's going to diverge, it's not going to converge to a value. We're going to look at how we deal with infinity for our upper limit and infinite for our lower limit, or when both of our limits are infinite. Well, what we'd have to do there is kind of break it up into two separate values. One, we've got a lower limit that's infinite, one with an upper value that's infinite, where we're choosing some value c in between negative infinity, infinity. It can be any value. 0 is a good one. And we're going to break it up and take each one individually. We're also going to look at functions where, hey, maybe it's discontinuous somewhere along the interval. We're going to see how improper integrals will also help us to find sequence and series later on, where we're talking about integral convergence and looking at how we can actually use improper integrals to see whether or not an infinite series will converge or diverge later on in our study of integration and also calculus.